you scored the padding and you were interviewed by the New York Times.
Yeah.
You didn't make it to that, but
Yes.
Will tell us more about that theory. So.
Cool. Yeah. Are we good?
Yeah.
Yeah. No pressure. Yeah. So this is going to be 0 to type theory in 1 hour. So I don't know how experienced everyone is with type theory. I'm assuming that all of you know quite a bit, but just in case, I'm going to start at the very beginning. I've been told that it's better to ramp slowly up than to lose everyone in the first 5 minutes. So that's going to be the philosophy. Okay. Let's see. I just made these slides pretty recently, so I don't remember what's on the next slide. All right. Here we go. So we got 3 statements. They have something in common. I'm going to ask you all to figure it out. First, computer science finally let us formally verify proofs. Second, type theory is an advanced branch of mathematics with esoteric proofs. And their proofs are esoteric artifacts that hold universal laws. Anyone have an idea? Yes? Right?
I was going to say false.
Not only false, but...
I just think it's a criminal lack of hanging indents. Because those double quote marks need to be off to the side, so the C is over you.
Okay, yeah, I will run my slides by you from now on.
Something you heard software engineers say.
Well, I think you got it. They're all false, but they're all backwards. So, in some sense, computer science exists because of formal methods. And I'll go into exactly how it is in the future. Second, you really don't need to know much math to understand type theory, and in fact, I think that the most difficult part for most people is just how simple it is, and how little grasp you can get from using other techniques to think about, the very base of it. And then connected to that, proofs are social artifacts, and formal methods are ways to develop more and more trust in those artifacts. But at base, it's, do people trust what I'm saying, and do they have reason to believe that it's true? Anyway, all right. So, recently at a conference, I got asked this question by someone who knew nothing about Lean, and I had to stop for a while because it's actually a really tricky question. So, in some sense, formal methods and proof existence are the reason that computers exist in the way that we think about them today. And recently there have been, of course, a bunch of developments with Rock and Lean and whatnot. So I'm going to go through the historical reasons that these things exist, starting at kind of some arbitrary points. And that should hopefully motivate some later discussion of, like, why do we care about type theory? What are these paradoxes, and what do they have to do with, everyday mathematics? All right. So first, I'm just going to choose to start in 1879 with Frege. So he wrote this book with this beautiful syntax that nobody uses, which is kind of a shame. It's beautiful. But this was the first appearance of quantified variables. So you have things like for all x and for all p holds x.
Can you replace a Google with a Frege?
maybe. Yeah, so this represents the starting point of analytic philosophy. Anyway, yeah, so from here, there's this kind of historical pattern of just fuck around and find out, where we propose these systems with nice notation, and we usually think that they're sound, consistent, that they can eventually prove everything that is true, and then someone finds a paradox, and then you make a change, and that's kind of a large part of the history of type theory from now on.
What was Frege trying to do?
Nothing less than develop a set of axioms and a notation for formally specifying logic. I guess, any more questions? Is this too basic? Is this too advanced? No? Cool. All right. So, Russell's paradox. This is in response to Frege. You might notice that there were about 22 years between when this was proposed and when this paradox was publicized. So the basic idea behind Russell's paradox, I'm not going to explain the whole thing, it has to do with quantifying over all things. So you can say things like, the set of all sets that do not contain themselves. So that's what this is. You have X, which is supposed to be implicitly quantified. So you have X does not contain X. For all of those things, this is set comprehension. Take all X's such that X does not contain X. So if you think about what happens here, I'm sure you're familiar with paradox, but if X is not an X, then it is in X, and vice versa. So the received wisdom from this, at least within type theory, is whenever you can quantify over all things, you can usually do bad things. So this is going to motivate the discussion of universes later on. An interesting corollary of this is that Zermelo, so the Z in ZFC, also knew about this paradox at about the same time. And so this was really the start of the type theory, set theory, I don't want to say war, but the difference in opinions. And you've already heard from Elliot, so let me talk about the other side. All right. So after that, there were these two huge mathematicians that, Hilbert is, it's like the emperor of mathematics back then, had this philosophical disagreement. They're both pretty stubborn, but, Brouwer ended up being kind of ostracized because he took the side of intuitionism, which is a very strong version of constructivism, against Hilbert's formalism. So what do those mean? Well, formalism is Hilbert would set out to exhaustively specify all the axioms for example, geometry. And the idea is you have all these axioms, you can combine them in whatever you want, and they will eventually encompass all of the true things about geometry and none of the false things about geometry. Brouwer basically said, some of those axioms allow you to tell me that constructions must exist without actually handing them to me, and that's not good enough. So the idea behind intuitionism and largely constructivism is if you claim that something exists, you have to actually hand me the thing. So this is, it's a philosophical distinction, and the larger distinction is, so I'm repeating this from a professor. Anyway, Brouwer kind of stands on the side of proofs are human communication artifacts, as in you really have to help people understand exactly what you claim to exist, whereas Hilbert is more on the side of, we should figure out all the true things, and anyway, this will become clearer later on, but there's this distinction, and sort of ironically, type theory has largely coincided with Brouwer's view, which I'm going to stop this. We'll get into this later on. All right.
Why, starting from the premise you said that proofs or human artifact that communicate to each other, why does that mean it has to be constructed? I guess missing that word. Because formal proofs can also be a communication tool.
Yeah, it doesn't necessarily, and this ties into a lot of the discussion around the axiom of choice. So we have, for example, theorems like in game theory, there's always a Nash equilibrium, but we don't necessarily know how to find it. And so that's a concrete place where these two would disagree, where in intuitionistic logic, you couldn't prove that there is always a Nash equilibrium because you can't show it to them. Whereas with formalist view, you can say there always must be one, and so there always is one. Whereas constructivism rejects a bunch of equivalent axioms of that flavor. Does that make sense?
Yeah.
Okay. Cool. Any other questions? All right. This seems a bit abstract. I didn't do a great job explaining it, but in the interest of time, I'm going to move on. All right. So Hilbert set out a bunch of problems for the mathematical community. It's a huge research program that practically everyone who's anyone worked on. One of these was the Entscheidungs problem, which is basically, in modern parlance, is mathematics decidable? Like, is there a machine where you can take some statement S, run it through this black box, and then get either yes, S is true, or S is not true, and ideally a logical proof that S actually is true or is not true. So the interesting thing about this is this is phrased as a effective procedure. So there has to be essentially something in the box. This is before computers, so someone can just follow a set of steps, and you have to write out what the steps are. So a lot of the process of solving this problem is not cannot really proceed until you find something like what is an algorithm. So that motivated lambda calculus. It's not well known, but the lambda calculus is a fragment of what Alonzo Church was trying to develop, which was a logical system. The logical system that he developed was proven inconsistent by Klein and Rosser in 1935, but this survived because it's a very, very good model of what we think of as all possible computation. And it's remarkably simple. It's just either variables, lambda abstractions, or applications. This is equivalent to Turing machines, and the Church Turing thesis says that any kind of computing machinery can be reduced to a Turing machine, which is equivalent to this. So this is pretty remarkable. Way back in the day, way before computers were practical objects. Anyway, so Church and Turing were working on the Enchinings problem. So this is often forgotten in CS curriculums. So the basic thrust behind this argument is that to show that the Enchinings problem is not true in general, you just have to pick out one specific problem where you can't make the thing in the box. And that one specific problem is the halting problem. So, the thing that we all learned about the CS curriculums, for those of us who took CS, was really just kind of a toy construction in the middle of what they saw as a more interesting proof, which was in the realm of pure math and formal methods. So that's kind of, it's a provocative statement, but that's why I said that formal methods are the reason that computer science exists, because this is kind of the modern foundation of computer science. Very briefly, I think it's a long paper, but you can get kind of 80-20 by just looking at this paradox. So if you say the Enchinings problem is solvable, there exists some black box, then you can use it to solve the halting problem. If you can use it to solve the halting problem, then you can write the Turing machine that solves the halting problem. You can write this as a Turing machine. And if you run it on itself, and you ask, does this paradox halt? Then if it says that itself halts, then you loop forever, you don't halt. And if not, then you return immediately. And so this thing always produces a paradox, and so therefore, Enchinings problem is unsolvable. So, the brief upshot of this, to be provocative, is that CS Sturgeon is side quest for formal verification. Cool. So I'm just going to survey the audience and say, is this a good case? Yeah? Okay, cool. All right. Inference rules. This is the thing that everyone tells me not to do, and everyone tells everyone not to do, but they're not scary. And so I'm just going to spend like 5 minutes showing you what inference rules are, how to read them, because you're going to see them if you're looking at type theory, and they're really not scary, but nobody ever explains how to read them, they just assume. So I'd like to, do what I wish that someone had done for me 3 years ago and explain this thing. So here's an inference rule. You've got a line, a bunch of statements on top, and there can be multiple things, but 99% of the time there's one thing on the bottom. And so the way that you read this is if P and Q and Z is true, then you can infer that C is true. And so you might be wondering why there's a line here. I'll get to that in a bit. But the nice thing is that it's kind of symmetric, where you can read top to bottom as because PQ.C is true, I can apply C. And if you have something like this, then you can say, I know that C is true because of PQ.C. So you can do things. Yep.
Leading question. This is also what we call conjunctive normal form, because there's just like a series of premises and it's always ended.
Yep.
The way that you've written this, would this mean that P, Q, and Z are all known as well as the conclusion at the end, or are you forgetting them as you go to the conclusion? In this
I don't think I followed the question.
Well, do you still have P, Q to Z as well as the conclusion in the conclusion, or is that conclusion as like a logical state? Does that exist only as the conclusion you've gotten all the different Z's?
I think I know what you're asking. So theoretically, if you have P, Q, and Z up here, that means that you've derived P, Q, and Z. So you kind of throw them away at the bottom.
Yeah.
But since you've derived them, you can basically take the derivation and copy it somewhere else. And so there are systems where it matters that you're throwing them away, and there are systems where it doesn't matter. So technically you are throwing away PQ, but in most systems you can rederive them somewhere else by following the exact same thing you did. Cool, any other questions? Great, all right. So, why do we have the line? Because we can do something like this. So, this is the derivation tree. So if you look at, count up the number of lines, you see that there are really 5 inference rules used here. And so the names on the right tell you what rule was used to go from the top to the bottom, or from the bottom to the top. So here, for example, this is a proof that false or true, and true or false. So the cool thing about this is you can see this as either starting from nothing and building up to this theorem, or asking if this theorem is true and then showing why. So that's mainly the reason that inference rules are ubiquitously used instead of things like, literally writing and implies. You can do things like this. Is this relatively clear to everyone? Are there questions? Yeah.
Is there a relation between this and like abstract data constructors?
Yes. I'll get to that.
Because it seems like statement, bunch of construction rules versus the economy.
Yeah, you're on this.
Confirming, so far there's no time. Previous question notwithstanding. We're not.
Yeah, this is kind of, taking an outside view. If you gave, it turns how 100 years could we come up with a derivation tree. I think this one. Cool. All right. So, moving away from that. So this is something that you might see on a specific line. So this also probably looks scary. I promise you it's not scary. This is a turnstile, and so it means if A has type A and B has type B and everything to the left of the turnstile. And so I'm just using these to show operator precedence. Then you can apply, you can conclude that Z has type C. So this is how you would write typing rules. This is kind of meaningless at the moment because you don't know what A, B, and Z are, and there's no real structure here. But when we see typing rules, and I promise this will be over soon, this turnstile just means everything on the left implies the thing on the right. So it's kind of like a line, but laid out horizontally.
Is it just the same as the line but a different notation, or is it different?
It's acting like a line, logically, but we will want to have typing derivations where we say, something has type T because, and then there's a derivation above. So we write these horizontally so that we can have them above the line. But it's still the same, like if A has type A and B has type C, and then we can apply this one thing on the right.
Everything on the left is like context, and sometimes you kind of like conjoin all the context into like a context symbol, and you just have like gamma turnstile, and it means like anything that was known previously, and then you move to the next thing.
Yeah, but it sounds like it's not exactly like a line, which is similar. It's like you could.
They're different notation for the same thing.
They are.
The useful, and the thing that they're notation for is just all of the things on the left apply to the thing on the right, or all of the things on top apply to the thing on the bottom. We just write them horizontally or vertically, and with different symbols to denote that they're kind of part of different universes and things.
Is one of them like the large step and one of the small step? Like this, or like they're single steps in this derivation, and then you can combine them. Does that apply to both symbols?
So,
If you go to the previous slide,
yeah.
I can say from nothing, basically telecollapse this whole thing and say from nothing I have the final expression in the bottom. Because there are intermediate steps that I can skip.
You could, but it's useful to know that, like, for example, here there are 2 things above the line. Here there's 1, here there's nothing.
Actually, I can compress it into a single, like, nothing, line, 0, and so. Is that a valid notation?
You could, it's not a precise notation. If it's obvious,
And what
people
about
probably know what
turnstile?
you mean.
Is the turnstile, is that also not allowed then?
Yeah, so the turnstile, you can imagine that all of these would occur in derivations. So I think maybe we should work through an example. Okay. Do we have one?
Well,
Yeah.
very brief comment. If you go back to the previous version, here's that. It is a reminder that these are, I'm curious if the following statement would be true or help the slide move forward, that in the end, though, these are all still social tools to persuade each other as human mathematicians. If you simply wrote blank, horizontal line, and then the last thing on the slide, it wouldn't be very persuasive to anybody, right? Meaning this is a simple trivial thing we're proving. Like the point is to see that, saw that. So it's your choice matter. It's a matter of style, and it's that simple and hard. These are all the pieces of things we're going to find out. But yeah, just because you can mechanically rotate one to the other doesn't mean you show.
Yeah, true. So you could, you could write dot to dot. It's obvious that.
Right. But the notation exists to decide what is obvious, and what is obvious depends on who you're talking to.
Yeah, and this will be something that we can mechanize as a proof system. So that's that's why the precise notation matters.
The one question, just between each of the lines, there's notations. How does that apply in you have the turnstile?
Yeah. Between each lines, you mean stuff like this? Yeah. I guess you could name reasons that things have types. That's not something that's usually done. It's more like, so the turnstile kind of acts like the and here, where it's within the language of the things that are below and above the line. And so once you have something that you know is true, you can kind of ignore everything that's above. So maybe I led you down the wrong path by saying that it's kind of like the line. Yeah, I guess for now let's just think about it as, like, let's say you're in the middle of writing quantity of a function, and you define some variables, and those variables have certain types. Then you can say it's valid that the return value for this function has some type, given that I use x, y, and z. So that's what the turnstile means. Given that all of these are in context and I know their types, then I can say that Z does have type Z, and Z might use A, might use B, might not. I think this will be clear if we go through an example then. So, okay, cool. I would also be happy to drop this if people are falling asleep. Okay, cool. So, here is a rule which says that if you have something in context, then you can use it. That's it. Here, this is falling below the line, and it's exactly the same thing. So if we have something like f has type from A to B, meaning f is a function that takes an A and returns B, that's already in the context, so we can use f as type A to B. And what this rule means, which is arrow elimination, I'll get into that one next. You can take an A, you can take an f, and if A has the type, the argument to f, then f of A has the type, the return type. So is this helping or is this hurting? Yeah.
So I'm trying to figure out if some of the notation is just like a mistake on the slide, or if that is doing something. So
Yeah. It's a mistake on the slide. This should all be down here, below the line.
It's line, right?
You can ignore this for now. So the way that, sorry. Yeah.
I think you can make progress. I'm getting usefulity here. I think of A as a point in two-dimensional space on an XY grid, a Cartesian coordinate system, and F is some function like distance from origin, like length, then like the length function, or the distance function. Then if I have A as a point in 2D space, then the left-hand side is saying I can use that, it's a point, 2D point. And the right-hand side is saying a function that goes from a point to a length, the function called the function called distance, will always, if I know that I have a point, will always return a single one-dimensional distance scale. And therefore, these things fall in logic. So in that very concrete term for us literal-minded people, is that I now know as a result that A is always a point, the function called length always takes a point and gives a distance. And therefore it entails the fact that the function called length takes in A and always returns the type distance. Sorry for being great pedantic. So,
Yeah, no, that part makes sense. The example. I'm still struggling with the why make it so complicated. Right? Like you have turnstiles and bars, and like obviously if you have A and apply F, you get B, right? Like the bottom line is clear why the syntax. So
well, the fact that you're taking your time to go through it makes me want to be pedantic and make sure I understand it. So this is a teaching style thing.
Yeah.
So why the two different?
Yeah, so that's a great question. The answer is because these derivation trees can get absolutely huge. What you really care about is the set of lines that you can use, the set of inference rules that are valid in the language. So a type theory is someone will say, here's 20 inference rules, and that's it. Those are all that you can use. And so you can use those rules to make derivation trees as big as you want. And we normally don't look at them, but they're sometimes useful, and people writing type theory papers love them. So this was supposed to be, let's teach everyone how to read them. I might have been a bit optimistic. But so,
I think it's like it's our fault.
no. It took me quite a while to learn how to read these things. So
it's not that they're unreadable; they just feel like extra complicated for no reason.
I think
It's not like it's very obvious what is the same.
Yeah.
But yeah, like why this formatting?
That's what Tara's on the first slide.
Like I get stuck on
okay, so-
implies versus turnstile versus
Yeah.
lines. Like you're just saying if then, but actually there's this important distinction that kind of matters for the formal systems.
Yeah, I think that's a good point. Like, you could write, have all of this at the bottom in parentheses, and then say, all of the things on the top also in parentheses with ands between them, and then like an implies, and the line would be like the length of this wall. So putting it on the top and the bottom of the line is kind of just a way to show a common thing that you do, which is just conjunction implies something. It's really under the hood, it's just doing exactly that. Yeah.
Sorry, I'm trying to guess from like something you briefly maybe said or maybe didn't say. So you said that there is a collection of actual rules that can annotate the horizontal lines, and that is part of the definition of the type theory, like this E here.
Yep.
So the point is that we are given a collection of primitives, and then we can build our tree from these primitives. And essentially, by convention, we're only putting the primitive derivations on next to the horizontal lines. And
Yes.
then the turnstile is a compressed thing where you have used a bunch of elementary moves, and you have you have derived a more complicated thing, and then you can abbreviate it with the turnstile. Is that sort of a reasonable take? Because that's what's happening here. You kind of like, you want to start with nothing, so you have to have this like, I guess you have to also annotate the top two lines with like nothing, whatever. Like if you have A, you can use A. There's going to be some annotation that allows you to do that, and then on this thing. And then you have another primitive move that combines them, and now you've built this tree that starts from nothing and gives you this bottom thing.
Yes. I think I really like what you said. The only thing I didn't understand was that turnstile is like taking a bunch of moves and kind of combining them into one.
Well, I mean, the evidence for this bottom turnstile is the tree that we have here. So, in a sense, the fact that we have the turnstile is a compression, of the tree that provides the verification that this turnstile implication is correct.
Yeah, I think that's a good way of looking at it. So the turnstile is like the core judgment that you get to conclude based on all the work.
Yeah, so like now, potentially I can forget the tree, and I already have the turnstile in evidence.
Yeah.
But like, in any point that I need it, I could in principle kind of substitute the tree for it or something.
Yeah, exactly. And the mathematical way of doing this is each inference rule is like an axiom, and you can recombine those axioms however you want, as many times as you want, cursively, and whatever you get at the end, it's the derived state.
I want to say one thing that I found useful when thinking about elimination rules, and I guess inference rules in general, and like let me know if this makes sense, is to think about them not as operating on like abstract like functions or types or whatever, but instead operating on like symbols on a piece of paper, right? And so when you see something on the top of the bar and something at the bottom, like it's literally saying, if you have the symbols at the top written down on a piece of paper, you can erase them and replace them with the thing at the bottom, which also kind of connects, I think, more clearly to the, computational notion of like, what it means to compute using these rules, right? Is it just a process of like erasing things and replacing them, or possibly expanding something into a bigger thing? I'm not sure if that helps at all, but
yeah, no, that's exactly, and that's something I should have said. So these symbols are defined by the way that they're used in the set of rules. So often people will have similar looking type theories in which the symbols really mean something completely different because you can or can't do something that you could have in the other system. So thank you, I really should have said that. The other thing is that whenever you see something like A and B, these rules are always maximally universally quantified. So this means, for any A and B, you have something like this. And so the rule at the bottom is basically just function application. That you can apply functions and you get the thing that they should return. I should have explained that at the beginning, and I should have explained the symbol manipulation. I think that makes things clear. I also don't want to lose everyone. Is this... Yeah. Okay, cool. All right. Great, so this is exactly the same thing. Before you saw arrow E, this is arrow I. So this means before we were taking a function and using it. So we were eliminating the arrow. So we, took the arrow up here, used the arrow, and removed it on the right-hand side. The way that you do that is function application. Here we're introducing the arrow on the right-hand side, so it's the I, by using a lambda abstraction. So for those who are unfamiliar, which I'm thinking is not anyone, this is the case, lambda is basically an anonymous function. So you say, this is the thing that takes some argument, which we call A. And then this B probably has something that uses A somewhere in it. So it's the only way of defining functions with a lambda calculus. Yeah. Thank you, that's where it's going next. So gamma and delta are, this is the last tricky thing. Gamma and delta are the common names for, this is a collection of terms and their types. So, if you crack open gamma, you might see A has type A, B has type B, C has type C.
So it's ordered list, basically, it's like before A and after A?
Yep, exactly.
So the order matters?
Yeah, why does the order matter?
So there are some type systems where the order matters and some where the order doesn't. And so the ones where order doesn't matter will include an explicit rule saying, and you can change the order. So everything is by default, these symbols literally mean these symbols in this order. And if you want to say that order doesn't matter, then you include a rule saying order doesn't matter.
Even writing it a simple prologue, maybe.
Maybe.
Very, like,
Well, this is from
around.
the 30s. Yeah, so anyway, I probably would not do end controls if I gave this talk again, when I give this talk again. But
I mean, if you read the paper in that theory, you have to see it.
Yeah, that's
There's less in.
that's the devil on my shoulder saying I should have done this.
I warned you.
Yeah. So the last thing I'll say is that this comma is overloaded because, I don't know, people are lazy when they're writing papers, and that really means you take gamma, you take delta, you can have it. Cool. Yeah.
Just to be clear, are gamma and delta here just two separate contexts because they're both in the assumptions? You kind of concatenate them both together and get like some super, like the set union of them, I guess.
Yeah, yeah, definitely. So you can kind of pattern match on the above. So let's say we have, Z, X, Y, A, and then some other letters. Then you would pattern match and say, okay, everything before A goes into delta, goes into gamma. Everything afterward goes into delta, and then you kind of use those in the bottom. Cool. This is, I believe, the last slide with rules, with lines of any kind. Are we good? Ready to move on? Okay, nice. I'm very happy with this. Okay. So, we've talked about things that have types. We've talked about how to assign things types. We haven't talked about how these programs actually do anything. So the reason that I drag you through this hell of introduction and elimination rules is because the way that you define computation, all you have to do is define what happens when you have an elimination rule applied to an introduction rule. And so if we go back, the elimination rule is function application for arrows, and the introduction rule is lambda abstraction. So if you take something like an arrow, it's a different kind of type, for example, like a product, it will still have exactly the same form of what happens when I eliminate something that I just introduced. So this square is just, I'm saying, any kind of type former, where type former means something like an arrow. So for example, in lambda calculus, the eliminator of the arrow applied to the introduction rule of the arrow means if you take a lambda abstraction and apply it to an argument. And so any computer scientist will say, well, of course, you take C and you plug it into A. And so that's exactly what this means. The kind of novelty here is all you have to do to define computation is say what happens for any kind of type former when you encounter exactly this pattern. The way to ensure that this doesn't go haywire is called subject reduction. And so that just means if you reduce in the way that you've defined, then the thing at the end better have the same type as the thing start with. So for example, you shouldn't start with a function that's takes some type and returns a string, and then you run it and you get an integer. So if inductively, anytime that you can run a computation, you end up with the same type you had, then in the end, when you finish, you're going to have the same type you started with. And so this is kind of the foundation of typed programming languages, especially functional programming. Cool. This is kind of a big leap. Any questions? Yeah.
No, I'm not sure I already asked a question. This question is it a common piece of notation to use the empty square for this? Or,
No.
Or is that actually a practical typo? I'm missing emoji.
I wish it were missing emoji. I would use like smiley face or something. No, I just use the square to mean put whatever you want within the square.
What's this?
C, I just use A, B, and C to mean anything.
Like, where's A on the left hand side? Like,
Right. So the reason that this isn't trivial and that you can just kind of knock out the limit intro is because, thank you for asking, the elimination rules and the introduction rules might have arguments. So for example, the elimination rule and introduction rule for functions are lambda abstraction and application. And to do those things, you need to provide arguments. So when you're eliminating the arrow that's in this type, you need to provide the function that you're using to do it. Sorry, the argument you're using.
Is that the same C right there? So lambda? Should we be a small C?
Oh, sorry, this means lambda calculus.
Oh,
In the specific example of lambda calculus, this is the beta reduction rule.
Yep.
So the elimination carried the C.
Yes. And so the reason that you don't normally see it written as functions like this is because there are implicit arguments and different type formers could have different implicit arguments. And so what you need to do is you need to define data reduction in such a way that you take all of these arguments that you need to run the introduction and elimination rules, and you come up with some way that they reduce such that subject reduction is. And this is non-trivial. Like, the arguably the hardest part of defining the lambda calculus or anything like it is how do I deal with names and how do I substitute the thing in the function when I call it. So it's very non-trivial, even though it's kind of beautiful that all you need to do is just take the elimination rule and the introduction rule and cancel them out.
Yes. Sorry, I'm now understand that I don't know what the implication arrow is. Like, so I know I'm combining, some of the primitive rules, and then what?
Right. So
it's the formula for, so it's like what I defined this. Sorry.
Yeah, I didn't explain that. So this just means I get to define how this thing
Combined.
evaluates to some
So
formula.
this is the definition of the beta reduction.
Yeah.
I see. Okay.
I think you suddenly went from explaining things slide by slide, step by step, to having a bunch of new terms thrown in at once. So you're going to start elimination, reduction, and then calculus. We're going to solve that.
Yep.
The point I'm taking out of the slide is that the thumb reader is that type former empty square here is being given as an example. In lambda calculus, the single arrow headed to the left is that this.
right? You're defining that concept. Like in your slides.
Yeah. Thank you for slowing me down. Yeah.
Is this a different or like a similar notion to the idea from previous slides of like you have some statements on a page, it's been erased and rewrite to something else? Is it the same thing? Or the computational judgments? Because you showed 5 judgments or 5, but they're also.
Yes. So it's a new kind of symbol manipulation that you get to apply.
Yeah. Does the previous thing like subsume this?
I don't think so. It's
If you just use elimination rules, thinking calculus, and introduction elimination rules, and you just do like statement rewriting, do you get this out?
I'm not sure I completely follow.
Or is that what different on this?
Can I have to translate your question? Sorry, so not with you. But you're saying this is a lofting of the game, saying if the game was, here's a game type with straight horizontal lines, and you're the prisoner in Searle's Chinese box, and all you're allowed to do is move things around in this horizontal line. Then the next slide is like, there's this other game you can play with this T-shaped looking thing that's on its side, tailnet. And then you say, well, now I want to play a game with like squiggly lines. Well, in general, you're going to be introducing some terms and eliminating some terms. In the case of lambda calculus, this is me teaching you, the idiot prisoner in the Searle's Chinese prison, this is what single arrow means in lambda calculus. So your point would be that that's what I hear when you say your question to Will is, does this slide subsume the previous 2 examples, or it's kind of an abstraction above them? So first I ask you, is my question even a translation of your question? No. Are you trying to say this?
I'm not sure.
Like, does this slide build on the previous 2, or is this slide an abstraction that replaces the previous techniques?
I think the thing here is because this one's using like the notation of function application, whereas the previous slide had like lines to do the deductions. The deductions seem to be operating by functions here.
Yeah, I think a larger point from this is that notations collide a lot, and I should have done a better job of pointing out when things mean different things. But this is extremely common in type theory papers. It's not always clear what things mean. But I think to answer your question, so elimination on the type level doesn't mean the same thing as like eliminating a function by applying it to it.
I think the root of my confusion is like the ontology context thing of like here you're trying to derive true statements using some introduction rule, and like you care about the truthiness of the statements, and then the lambda calculus, it's purely just rewriting. There's no notion of truth.
You postulate that you basically write rules to preserve truthiness.
So that's why I'm imagining thinking about sequence calculus. I'm like, oh, it's a system for deriving new true statements. Where lambda calculus seems like more like a component of that.
I think you're getting to something that I was hoping you would not get to yet. But okay, so I think I'm going to basically say that we've covered this enough. I haven't done a good enough job explaining it, but I don't think this is essential for getting through the rest of the presentation. So I want to go through something more concrete so that it moves on. Okay, cool. All right. This will be difficult, so I'm going to skip it.
Cool. You spent this whole thing arguing that the letter O and the letter R, that I think of as or, you're explaining that. That's always skipped.
It's a really cool thing about why computation matters for proofs, but I hope that we can get to it later. And I'm going to go through something more concrete so that we can kind of bring everything back to it. Okay, cool. I'm realizing that I'm no longer on my own computer.
Do you want like?
The terminal.
Yeah. Yeah. Give me 1 second.
Okay. And do you have Lean installed?
Yeah.
Or VS Code, or whatever you want. Yeah.
Actually, I was just going to break. If there's a break, can I ask a question?
Yeah. Please. This is difficult, and I haven't done a great job.
So the kind of like lambda calculus based type theory, it seems like, I don't know, not intuitive, but like, how to say, I sort of have an idea what it's supposed to be talking about. But you mentioned that there might be type theories where like the arrow is not an arrow, but like a product or something. So is there like a simple enough version somewhere? Maybe like I cannot do later, like because I think it would be illuminating to distinguish between like interpretation and formalism if you have more than one example, especially one where they sort of diverge a little. So like if I had something where this box was not an arrow but like a product, then I could see how the illumination and introduction work in that context and how their composition would correspond to some beta reduction rule, which is not just, application to a particular path, right?
Yeah. So
Are there such two examples that I want to look at?
Yeah, I can easily provide just verbally one example, which is if you look at like a pair. So you would take a type A and B and produce a tuple of A, comma B. The introduction rule would be applying the tuple to A and B, and the elimination rule would be taking the first element or taking the separate element. So there are two different elimination rules.
And so two different beta reductions.
Yeah. So you would say, if you have the pair A, comma B, and you take the first element, then that is better reduced to A.
Yeah.
And if you have a pair A, comma B, and you take the second element, that better reduced to B.
Okay.
And so that's exactly the same kind of formalism as function application.
Sure.
It's just the function application is a hell of a lot more complex. And that's where a lot of the interesting computation is.
In fact, you can build it out of function application, or you can also take it as a primitive.
Yeah. Yeah.
And you can build pairs with lambda functions, but also you can say they're primitive to zero.
Yeah, but I think that's more interesting from a point of view of like illuminating the whole formalism.
Yeah, and maybe I shouldn't have chosen lambda calculus, because the thing about the lambda calculus is, as you said, you can build everything out of just function application.
Well, I mean that's the core example, but like I think like having core example and a toy example together or whatever.
Yeah.
Anyway, thank you.
You're absolutely right. Yeah, I had an interview this morning and made these slides.
Okay.
Okay, I'm glad that everyone is still here. And
The setup is ready.
Okay. Cool.
Let me know.
Yeah, that's great. Nice. Great. So I was going to do this in Rust because it's not a very important language, but Lean's going to work. Or do you have Vim?
Yeah.
Nice. Okay. Cool. So who here is familiar with algebraic data types? Sure. Nice. Okay. So for everyone who isn't, it's something that you've surely seen already, and that is going to be immediately obvious. But it has a very mathematical name, and it has a name for a reason. So the thing you can do is to find something like, so let's say, this is already a type in Lean. Let's pretend it's not a type in Lean. So we can say, for example, if you have an option of some type T, then it can be either none or some constructor applied to some argument T. It's yelling at me that it's already been declared. So let's say optional.
Maybe.
Great. Computers are always trying to be helpful, aren't they? Okay. Cool. So let's ignore the risk. So yeah, this is a very simple example of an algebraic data type. So all that long name means is that you have potentially multiple ways to make a thing, and all of those individual constructors might take arguments. They might take different numbers of arguments of different types. So, for example, this is an option. You can have, let's say, list of some T, where you have, the empty list, or let's say, append some T, some type T, to another list, type list T. So it's the same kind of thing. Yeah, sure.
You have to get rid of the error first.
Yeah.
If you rename it to list one. It's fine.
But then which one is which
List,
one?
Type U1. Yeah, so we'll get to the U1 if we have time.
Do you want the other one to be list one as well?
Oh, the other one.
Good point. Great. So, in short, this is all that an algebraic data type is. it is the single biggest thing that I miss in languages that don't have it. It's extremely, extremely simple. And the nice thing about this is, for example, if you're writing a function that takes a list, then all you have to do is match on the list, and it can be one of exactly two things. You just have to have, if it's empty, then I do thing one. If it's append, then I do thing two, and usually a curse. So the power of this kind of construction is that you can build practically everything that is interesting out of algorithmic data. So, for example, you could, normally you have structures or records, which is just you have a bunch of fields and they're all the same number of fields. And so that's just the singleton, where the only constructor has type these things.
Is there an easy example of non-algebraic data type?
Yeah, you could say like a not only, but you could say, for example, a structure with submarkets. So the reason that this is non-algebraic, even though under the hood it is, but syntactically, it's because you're not enumerating all the ways that you can make it show. You're just saying implicitly there is exactly one way that I can. And what I'm saying is that's exactly the same as saying an algebraic data type with exactly one. Exactly one constructor. Is this making sense to everyone? It should be extremely simple. Cool.
I think the interesting part in Lean is not only all computation can be done in algebraic, but there's all logic that can be also done in algebraic.
Yeah, exactly.
So theorem proving is also.
Yeah, that is absolutely amazing. And to kind of
sorry if I saw you.
no, you're good. So there's a deep reason why it's called an algebraic data type. It has to do with category theory, but we don't have to go there. The interesting thing that you can do is you can write something like option T as an expression involving addition and multiplication. So you could say, for example, there is exactly one way that I can make none. So I would take 1, and then plus, there's a different way that I can make this thing. So plus the cardinality of T. So option T is in some sense equivalent to 1 plus T, in the same way that a power set is 2 to whatever, because the cardinality of the power set is 2 to the cardinality of the thing. So there's this notation where option T is equivalent to 1 plus T. List 1 is you have empty, there's exactly one way to make empty, plus all of the ways that you can append, that's plus T times list 1 of T. So this is kind of a recurrence relation where you're saying, this expression tells me exactly how many ways I can make something of this type. It's very, very deep. Briefly, I'll just say that if you take a partial derivative of this expression, you get a really, really interesting data type called zipper, which is the same thing but with one hole removed. It's not just like a cute notation. There's a very deep correspondence here. And so if you remember back to a few slides ago, where we had true and false represented as 0 and 1. So for example, true and true is 1 and 1. That's very common in logic. And the reason that that's very common is, 1, because that's how bits are made. But 2, if we think of 0 and 1 as algebraic data types, we can think of, okay, I'm going to write down 1. So you could say, I know that the algorithm to take this notation and turn it into a data type is you take all the pluses, all of those items from constructors, and all of the times from fields. So you could say, 1. So we know that 1 has to have exactly one constructor, and that one constructor shouldn't take any arguments since there's no multiplication. Cool. Now if you think about 0, we know that 0 is the thing that you can add to anything and not change. So the way that you write 0 is you have no constructors whatsoever. And so the point I'm going to make is that there's a very, very deep connection between these two very simple algebraic data types, and I'm going to move them up so that everyone can see. There's a very, very deep connection between these two data types and the logical word 0. How is that? Well, this is the part that I didn't cover when I skipped a bunch of slides. But the benefit that you get from encoding computation in your type theory or logic is that you get to say, if I have something of this type, like if I have something of type 1, then when I run the thing, when I evaluate the final value, it's going to have to form one of these constructors. That's the kind of soundness of the type system. So 1 represents a trivially true statement, 0 represents a trivially false statement. So 1 is trivially true because you can just construct it, and 0 is trivially false because there is no way to construct it. And so the way that you would say, is this a good type theory, is this a bad type theory, is can you make a term of type false? Which means can you construct, can you trick the type system into thinking that there's some value that I can't really create? So that ties back into a subject reduction, and if I run the thing, no matter how long I run the thing, it better have the same type at the end as in the beginning. Cool. Is this making sense? Nice. Yeah.
Do you want a quick test? Write false and command click on it. We can see
Yeah. Nice.
where we end up. Def.
That's not a problem.
Yeah. So we're going to see inductive where empty.
So that is exactly how false is defined. So the reason that I'm doing all of this, and the reason that I went down this rabbit hole of inference rules and all that good stuff, is going to show you what's going on under the hood in Lean. The reason that I think this is valuable, even though I think at some points I've lost a bunch of people who thought they figured out explaining, is because I kind of think you don't really own a car until it breaks down, you can open it up and fix it. And so you should really know, like, this is how false is defined. You should know how exists is defined.
We promise self-driving cars that never break down. Why do I need to read the prelude?
Well, I mean, Lean also promises you that the car will sound. You better go out and share. Cool. So I guess at this point, we're almost at an hour. Does everyone want to continue, take a break, go down some other path? Okay, I have more slides.
Is it a promise or a threat?
That's up to you.
Like
Also, yeah.
They are. There's a lot more inference rules. Cool. So there are more slides that are more applied and fewer inference rules involved. Here are the slides that I skipped over for you. Do you want to go through them? I don't think this is going to go well. Okay, all right, very briefly. I'm not taking any questions. If you get it, you get it. All right. So, for example, let's say we have, someone says, I have this great type theorem. I have this great type theory. And within this type theory, I have proof that A or B is true. Where, pick your favorite A or B, instantiate it with, Goldbox conjecture, whatever the hell you want.
Natural numbers even or odd.
Yeah, sure. Yeah. Every natural number is even or odd, or the Riemann hypothesis is false, right? And they say, I have this great type theory where either this thing or this thing. What we want to do is we want to make sure that that or within the theory really means or in plain English outside the theory. So you shouldn't be able to prove that A or B without showing me a proof of A or showing me a proof of B. And so the idea is you should be able to take the entire derivation tree of A or B and look above, and somewhere in that derivation tree, you would better be able to find either a proof of A or a proof of B with no preconditions. That can make sense? Okay, cool. And I'm not in the presentation. Cool. So that's exactly what we said, where you take, this is the final line. Below this, you have A and B. You have no context, so given nothing, I can show you that A and B is true. And these dots mean there's some derivation tree. You have to figure out what's in it, but whatever is in it, it better have a proof of A or a proof of B. And so what we can do is, because we have a finite set of rules, we can look at, all right, well, how could this have been created? So we can kind of iterate over all the possible rules that could have had this at the bottom and induct on that. That's the basic proof technique. So the emoji is not rendering, but this should be a green checker. So this means if we take the or rule, where you take whatever's on the top and you throw it on the left, and you get to put whatever you want on the right. So that's or left. Yeah. That checks, because we have this on the bottom. If we apply or left, then we know that has to be on the top. That's for today, so we're good. Similarly, we can do the same thing on the right. And the thing to notice here is that, for example, you can't have an and rule, because the ands couldn't have an or at the bottom. It just wouldn't work. So you have to kind of pattern match and say, what inference rule could I have used in the other thing at the bottom? And there's only one such more inference rule. This is the problematic one. What if I had some hypothesis? Again, sorry about the typographic issues. What if I had some hypothesis called C? We don't know anything about C. But I used C to prove that A and then over here I proved C. So the problem here is we're inducting on things that have or on the bottom. We don't know anything about C, so C might be a proof of random hypothesis. That doesn't have the shape or, so we can't use our inductive hypothesis. So we're kind of stuck where we have this hypothesis that we don't know anything about, and it's killing our inductive procedure. But the thing to note here is that all of the other applicable rules work. So what can we do to get rid of this? So the idea is we should be able to take the derivation tree that uses C and come up with some equivalent derivation tree that doesn't use C, so that we can show that within that one there's a proof of A or B. So how do we do that? Well, if you look at these issues. So if you look at, for example, here we have C implies A or B, which is the only way that you can get something like C on the left implies A or B on the right. Then we're good.
So is the problem with it on the left or on the right?
The typographic issues on the left.
No, not that problem.
No,
The problem
sorry.
we're trying to solve, we're trying to find, do we go left or right? It's all on the left, right?
Yeah,
So I'm taking this and
Yeah.
I'm blowing it up to full
Yeah,
size.
I get it.
And then the problem is kind of the whole thing at once.
Oh, I see.
So we have,
The right side.
Well, we're not going to find the proof of A or if we prove it on the right. We're
So
only
we
going
have
to
to
find
go
it on
left.
the left. So we have argued that we'll find it on the left.
but even if you find it on the left, it still probably has C in it.
Yes, sure.
And so you can't show that.
Yeah, but then you need to eliminate. You need to like maybe take the one on the C and like use it to eliminate the C on. Is that the idea?
I think you're going where I'm going,
Okay.
which is, so we have, we introduced some hypothesis C, we proved it over here, and then over here we used the proof that we came up with over here to prove A or B. So what we should be able to do is realize that we just eliminated something we just introduced, and take the C over here, the proof of C, and kind of inline it on the left.
Yeah.
So we can take the full proof of C
Yeah.
and inline it and remove C from the bottom. So the way you do that is with something like this, and you should be able to cross out everything that's there. And then if you look at what we just did, that's exactly data reduction and subject reduction for proofs. And so if that makes sense to everyone, I kind of pulled the wool over your eyes and said, we have this thing we want to show, which is that these axioms mean what they mean in natural language. And the way that you prove that is by introducing computation on proofs. And that's kind of, it's a very deep thing that I'm trying my best to explain, but the typography is making it difficult. So this is kind of an informal argument for why we should care about computation. It's not necessarily the case that computer scientists just wrote these proof assistants and include computation because they could. It really, really helps with, even if you aren't running programs, you can show that nice property of X. Okay. I said I wouldn't take questions, but I think that went better than I thought. So, yeah.
Quick question. If you have the function C to A or B, why don't you instantiate that as that is a thing, and look inside it? Is that are you not able to do that, or surely we just look inside the procedure that takes you from C to A or B?
Two things. First, I should have noted that this is just logical implication.
Yeah.
And then second, if you want to look inside C, then what you're doing in the middle of the proof is kind of, this is an induction. And if you were to look inside C, you would be running another induction within that.
But you can't look inside the implication. Generally, no.
You can, we go back and do this in slight bit more detail. If you look at all of the ways that you could have come up with C implies A or B, there are exactly two ways. So the first way is you have C on the left side of the turnstile,
Yeah.
and you just do the syntactic rewrite, which just arrow means the same thing.
Okay.
So it's a C. Or, this is the problem, you could have another hypothesis D that tells you that C implies A. And so the problem just keeps getting worse.
Ah.
And so the only way to resolve that is to say that for any proof, I can run it by substituting in proofs of things that I already know exactly where the hypotheses are used. Yeah.
Just kind of getting back to the thing before where it's like antagonist is embedded in here.
The rules are very similar. Yes. And
Are
there's
they
a
not,
deep
are
reason.
they not the same?
They are exactly the same. Yeah.
So it is embedded. Like you're redefining the rules of antagonist, using the rules as antagonist.
The thing I wasn't going to tell you is that the rules happen to be exactly the same, but nobody wrote them down. The rules for simple logical implication and for calculus are exactly the same.
Very powerful.
Yeah, exactly. It's a great how it goes. Yeah.
What are you assuming about the context in this argument? Like, if A or B was literally in the context, then A or B gives you A or B would not allow you to pull out A or pull out B. So, what does the beginning look like here? Just to know for sure that A or B just wasn't already there.
Yeah, so that's, okay, thank you for asking that. So that's, if there's nothing to the left of the turnstile, that means that there was absolutely nothing over here. And so the idea is to kind of prevent what you're saying by saying, the rules that you give me for your type system, for your set of implication rules, can't introduce something like that because it would be unsound, because I would just do simple things. So the idea is you start with a proof that nothing implies there, meaning that there would be always holds. And you have to verify that you really proved either A or B. So is that kind of
So
what
you're
you're saying? Like you shouldn't be able to just introduce the same formula.
Okay, so the claim is that so we're looking at tautologies. A or B is it's only possible for A or B to be tautology if at least one of A or B is a tautology.
I think you get to define what the symbols mean. So it's kind of the game is saying that these symbols mean what you want.
What's something you can derive? What is a derivation that can be done from absolutely nothing here? Like, what is a situation in which we have blank turnstile A?
It depends on the rules that you get. So you could say, for example, like if we're working in, intuitionistic propositional logic, then you have a different set of axioms that you use. And if we're working in classical logic, you have a different set of axioms. And so the idea here is like, you're given some derivation tree, and you don't know what the axioms are, that you can run induction. And so the idea is like, it should mean what you think it's a tautology. Yeah.
And the whole premise was like, we really wanted to know where did it come from, the left or the right.
Yep.
So doing classical mathematics, you have